Okay, so yesterday we looked at discrete probability distribution, and I kind of lied to you a little bit. I said that we would wait till for continuous probability distributions until like math 35. But I lied, because normal distributions are really continuous. System of math 35 will look just at general cases. It uses more energy to do that. Probably you've heard about with tests in university and stuff like that, the bell curve. Okay, anyone heard that phrase? A couple of you, yeah. So that's what we're going to look at today. What is the bell curve? Really what it's called mathematically is a normal distribution. Okay? So that's what we're studying today and tomorrow. Normal distribution. It means with all the data that you have, if you were to graph it in a probability histogram or spike graph like yesterday, and so we join up the tops, join the spikes, it would form that bell-shaped curve. Okay? And so what happens is, if you think about a histogram, that means the highest bar is in the middle. So the median is there. If it's equal on either side, that'll be very similar to the mean, the average, and the mode. Obviously, the highest bar is the mode. So in a normal distribution, those three values that we know how to calculate are approximately the same. Okay? So that's, in essence, what a normal distribution is. So, if we take a look at physical measurements, such as length, volume, mass, for certain data, that will follow a normal distribution. Some things won't. Okay? Not every set of data follows a normal distribution. We've seen graphs like that, histograms. We can't do everything. We can't answer a whole lot of questions about those. As you learn more, if you take stats, if you take math 5 or take stats in university, you learn more about different distributions. We're concentrating on data that forms a normal distribution. Okay? So these are the histograms. So weights of players, heights of math 30 students, lifetimes of light bulbs, hours of study. So you can see if you join those up, they look like a bell, a church bell. Okay, think about that. So, that's the bell curve, the normal distribution curve. Okay, next slide. Here's an example that we're going to look at. Got a whole bunch of data. We're going to fill in the chart, fill in on the bell curve, and do some calculations to see how it does follow that normal distribution. Okay, so this is light bulbs, looking at the lifetime of them, how many hours. So someone tested 44 bulbs, and so there's 44 entries here. Okay, calculated the mean life of the bulbs, and to be approximately 900 hours, and the standard deviation to be 50. Okay, so they all have slightly different, but those are the values. So I want you to look through here, prepared a chart where it's set into intervals. So look at all the data values and see how many are less than 800. Okay, now, first of all, look at these. I think they're all in order. Nope, not quite. Of course. Okay, so go through. So that's less than 800. 800 to 850. 850 to 900. So include in here, we'll include 800 to basically 849.99. And then 850 to 899.999, etc. So you go through that and then determine how many data, what percent of the data values in each one. I'll give you a couple minutes to do that. Okay, so 44 data values, so 1 out of 44 times 100, and 2 decimal places is 2.27%. 6 divided by 44 times 100 is 13.64%. This would be the same, because it's already calculated for you, for 15, as with these ones. So 6 is 13.64, and 2.27. So in the middle, it's very symmetrical, right? Between the two middle intervals are the same. These are the same. These are the same. As you see out there. Okay. So you were told, you didn't have to calculate. You were told that the mean, that mu symbol is mean. You can use x with a bar as well. That's 900, and you're told the standard deviation is 50. So it says write the following numbers in intervals in terms of mu and sigma. So if mu is 900 and sigma is 50, then 950 is mu plus sigma. Kind of working backwards from numbers to symbols to variables. Okay. 850 would be mu minus sigma. 900 minus 50. 800 would be 900 minus 2 times 50. Okay. So you have to show it in terms of mu and sigma. 975, well, what would that be? That's mu plus 75. Well, our sigma is 50, so we need 1.5 of them. So that could be 1.5 or 3/2. In normal distribution, we do use decimals. Okay, so I'm going to show it as a decimal. Now, the next part says 900 to 1,000. Basically, show that interval. So here, we'll keep the word 2. So this would be mu, actually just mu, sorry. Because 900 is the mean. 2 mu plus 2 standard deviations. Just 50 is 100. So again here, 850, well we did that already there. That was mu minus sigma. I'll put brackets around it maybe, just to make it easier to see. Okay, because it's 2 terms. And then 1,050 would be the mean plus 3 standard deviations. Because 50 is 150. Take a look at this curve underneath, okay? Notice how the data values are graphed here, okay? 900 is the mean. It's right smack dab in the middle. It's a symmetrical graph, this bell curve. 950 is the next good unit. So we have to go up by 50s. So this would be 1,000, and this would be 1,050. Okay? So going up by 50s is good unit. So that means this would be 850, 800, 750. Okay, so we always start in the middle with your mean, and then it was already labeled for you. 950 is the next good unit, so you know each good unit is 50. take a look at this labeling here. What this is saying is the percent of the whole bell occurs in this part of the bell, okay, between 900 and 950, 34.09%. Well, that's this, 39.09% is between 900 and 950. Same on the other side. Okay, so you can fill this in, 34.09%. Then from 950 to 1,000 was 13.64%. Same on the other side. And then 2.27%. And the next one. Notice how the graph does not touch the horizontal axis. Okay? So there is right here and a gap. Why is that? Because it could be outliers or values beyond 1,050 or below 750. So if we make this go right down, in this case, there isn't anything here, but we often use this curve to generalize huge groups of data. Okay? And so the way you draw it, you just leave a little gap. So the mean will smack dab in the middle, and then 1, 2, 3 standard deviations on either side is how you draw a normal distribution. Okay? If we take a look at those expressions we did in terms of mu and sigma to graph them here, remember 900 was mu. So that's the label underneath in this row. This is mu plus sigma. This is mu plus 2 sigma. This is mu plus 3 sigma. This is mu minus sigma. Mu minus 2 sigma. And minus 3 sigma. I'm just labeling it those vertical lines in the graph. Okay, so note the curve is based on one particular example, the light bulbs, and is a good approximation for the standard normal distribution curve shown on the next page. So if you take a look at the next page, that shows you basically the exact standard normal distribution. Okay, in terms of some notation, if you are given a group of data and you see this n here, it means it's a normal distribution. In brackets, the mean will be given to you as sigma squared. So that's the standard deviation squared, which is the variance. You don't really have to worry about that in this course. You go into Math 35, then notation, you need to be aware of it. Okay? So, in order to compare normal curves to solve probability problems, we convert the normal distribution curve into a standard normal curve and answer the questions appropriately. We'll get to those. Take a look here. This is actually the function. You wanted to graph that normal distribution. You would put that in your graphing program, calculator, or whatever program you're using. That actually graphs the curve. So the area under that graph is going to be 1. Okay. All right, so it says verify. We're not going to spend the time doing that for right now. You can do that on your own. Okay. So the diagram underneath here, I'll outline on the next page, shows the approximate area under the standard normal distribution curve subdivided into regions, equal width. Those are equally spaced. Percentage of the area under the curve in each region is indicated. Okay, and there it is. It's a little, yours is a little bit bigger. Okay, so that example percentage here, 0.13%. Very small. That could be anywhere past 3 standard deviations. Okay? But it's all symmetrical. You do not have to memorize these percentages. Your calculator is going to do everything for you. Okay? So don't memorize them. What you want to realize is that it is symmetrical. And then it goes 3 standard deviations either way. Okay? So let's think about these questions here. It says complete the following. What percent of the data is above the mean? Remember, this is your mean, your median, and your mode. In any case, if the mean is right smack dab in the middle, what percent is above the mean? 50. Okay? Then it says, what percent of the data is within 1 standard deviation of the mean? So that would be all of that area. Within 1 means you have to look where you add 1 to the mean and where you subtract 1. Okay? So that would be 34.13 doubled, which is what, 68.26? Two standard deviations of the mean would be there. So it would be what we already have there, plus twice 13.59. Let's do 2 times 13.59 plus 68.26. Okay, within 3 standard deviations of the mean, okay, is the majority of it. It's everything except these 2 parts, or what we just calculated, plus 2 times 2.15, however you want to do it. So to take that and add 2 times 2.15. So, in a normal distribution, 99.74% of the data will be within 3 standard deviations. Right? So plus or minus 3 standard deviations. So almost all of it. The odd time will be a data value above or below that. Okay? Then, what percent of the data is between 1 and 2 standard deviations? So that would be this here. What percent of the data is between 1 and 2 standard deviations above the mean? So that's that, 13.59. Between 1 and 2 standard deviations below the mean is the same. It's the same part, just 1's above, 1's below. Look at the last one. Alright, so again, you don't have to memorize all of those. The calculator will be able to do that for you. Okay? Some basic properties are listed on the next side. So the total area under the curve is 1. Right? So area is 1. Percentage-wise, that's 100%. Okay? So area is equivalent to percent. Right? So in your calculator, it's going to give a value less than 1. If you want to convert it to a percent, you multiply by 100. Okay? It does extend to infinity, left and right. It doesn't touch, remember? The normal curve is symmetrical about the mean. 50% of the area under the curve is to the left, 50 is above. All data is represented by the area under the curve, and the mean, median, mode are the same value. So, it says here, post-secondary studies, you may come across data that is skewed. You In this case, some of the above points no longer apply. Skewed means it doesn't look like a normal curve like that. Maybe it looks like something like that. Okay? That's skewed to the right. Right? So we're not studying that this year. Okay, so first example, a nurse reports the number of hours an infant sleeps during the day. She then reports the data on the normal distribution curve, shown below. The values shown on the horizontal axis differ by 1 standard deviation. So the data values are shown. They differ by 1. So that means this is your mean, right? Right in the middle. This means the difference between those two is the standard deviation. So your standard deviation would be 2. 14 minus 12. So the mean is 12. Standard deviation is 2. What are the values for A, B, C, and D? Well, just label them on here. It says the values shown on the horizontal axis differ by 1 standard deviation. So that's a standard deviation. Another one here would be 16, 18. Then we're subtracting 2 each time. Okay, so A equals 6, B equals 8, C equals 16, D equals 18. Okay, now we're going to learn how to do this on a calculator. For now, just look to the left of your page. Okay, with those percentages, it says what percentage of days does the infant sleep 12 between 12 and 14 hours. So we want to find the area of that piece, which if you look on the left of your page, here it's 34.13% or 0.3413. Okay, and we're asked for percent, so that's going to be 34.13%. So for right now, we're just using that normal distribution curve. It's given to you. Between 8 and 16, well, that's 2 standard deviations below to 2 above. We actually already summarized 2 below to 2 above. Within 2 standard deviations of the unit. So it is here 95.44. Okay, and less than 6 hours is that little bit below the 3 standard deviations. So if we take a look here, that's 0.13%. Okay, then it says, why is it not possible at this time to determine the percentage of days that the infant sleeps for less than 13 hours? So 13 would be halfway in here. Can we take half of that percent? Yes or no? Can we take half of that percent? No. Why not? It's curved. It's not a histogram. If it was straight across there, then yeah, you take half of it. But this is curved, so we don't know. I mean, yes, we gave you that function, but you don't really want to work with that yet. So we don't know enough information. Really, it's not half of that. That's area. Okay. because we don't know what the area is from 12 to 13 hours, the normal distribution curve is not a rectangle of a histogram. So you can't just cut it in half. Now, we're going to learn about z-score. It says to answer part E, we need the concept of z-scores. You don't have to have the concept of z-scores, but we need to learn about them for other problems, so we're doing that next. And now our calculators will do either method, with z-scores or without. So we'll go through that as well. Okay? So, what is a z-score? That's the big question. So a z-score for a data value describes the number of standard deviations above or below the mean. So basically, it means that you can calculate things without knowing what the mean or standard deviation is. And this is how knowing about z-scores will help you calculate things like how they change marks at university on a bell curve, so that everyone is still in the bell, okay, but maybe closer together because they lower the standard deviation and then they move the mean higher. In our math IB, we do a mark adjustment that everyone gets the same, right? So everyone goes up. In a bell curve, not necessarily everyone goes up. In science, when you get, if you're taking IB physics, I think Mr. Watt does a mark adjustment based on z-scores, based on normal distribution. So it's something that actually does get used for that. Okay? So, consider class example 1 with a mean value of 12, so the number of hours per baby sleeping. Standard deviation of 2. Okay? So 16 is how many standard deviations above the mean? Well, that's 4 above the mean, which is 2 standard deviations. So the z-score is 2. So however many standard deviations tells you what the z-score is. Z-score is a real number. Okay, it can be positive, negative, it can be a decimal. You don't actually use fractions that often. All right. Actually, I should say a rational number. We never use irrational score. Data value of 6 is, so that's 6 less than 12. So it's 3 standard deviations below the mean. So it's considered a negative z-score. And so that expression, it would be mean minus 3 sigma. 12 is 0 standard deviations away from the mean. So the mean has a z-score of 0. Nothing's been done to it. 13, that's a half a standard deviation, and that is above the mean, because it's greater than 12. So the z-score is 0.5. Okay. So, I'm just going to do this. Okay, so now let's label these here. So in terms of mean and sigma, well actually, I'm going to go back, it's so tiny. Okay. Alright, so here, that's your mean. Okay, this is your mean minus sigma, mean minus 2 sigma, mean minus 3 sigma. Here, this is, I'm just going to put it underneath because it's going to get squishy. Mean plus 0.5 sigma, mean plus sigma, mean plus 2 sigma, mean plus 3 sigma. So what are the z-scores? They're just the coefficient of sigma. -3, -2, -1, 0, 0.5, 1, 2, 3. Okay, so how can, for a particular value, say you said that a baby slept for 14.6 hours. Okay, how do you figure out what the z-score is? Or how many standard deviations? Same thing. Well, you want to find the difference between that value, 14.6, and the mean. So that would be what, 2.6, and figure out what fraction of a standard deviation that is. Okay, the standard deviation is 2. This 14.6 would be about here. So what fraction is this out of the whole thing? Okay. Well, actually, sorry, I'm looking up. It's thinking that maybe give me 1 sec to fix this one. Okay. So here, if I'm saying 14.6, it would be there. So our standard deviation is 2. So yeah, I guess that's what it is. So this is 2. This is the difference actually with all of this. So this difference from here to here would be 2.6 divided by the standard deviation is 2. So that's going to give you a value of more than 1 standard deviation. So a z-score more than 1. So you want the difference between those divided by the standard deviation. Okay? And you'll get that formula if you need to, if you don't like memorize it. You should try to memorize it. Okay? So let's practice on that. So the heights in centimeters of 5 starting numbers of the Wolfhounds basketball team are given. Mean is already calculated for you, as is the standard deviation. Calculate the z-score to the nearest 100 for each one. So first one's done for you. There's the formula. So z for the height of 170. Keep it in order because z-scores can be positive or negative. So there's your data value. Subtract the mean. You get a negative value. That means your z-score will be negative. Because 170 is less than 190. Any data value that's less than the mean will have a z-score that's negative. So subtract that and divide by the standard deviation. You get negative 1.33. Next one would be z of 182. So 182 minus 190 over 15. And you can calculate these. Okay, next one. Tony's midterm marks are shown below, together with the class, mean, and standard deviation for each subject. By calculating z-scores, determine in which subject Tony performed best relative to the rest of his class. So it says calculating z-scores. So once we calculate the z-score, for math and physics, how are you going to tell which is going to answer this question? Okay, how performed best relative to the rest of this class? What kind of z-score are we looking at? First of all, we're looking for negative z-score. No. So then we're looking for positive. Okay? We want a big positive or a little positive? Big positive. You want that to be far above. Okay? So we're going to calculate. So z-score for math. Okay? Here is 74. Mean is 68. So we scored above the mean, right? Standard deviation is 12. Then we scored above the mean. Okay, as well. And physics scored just above the mean. Okay, but smaller standard deviation, but likely not enough smaller. Okay. So these were 6 apart, right? These were 6 apart, but standard deviations were a little bit different. Okay. So 6 divided by 12 is 1.5. So that's a z-score for math. 6 divided by 14 is a little bit less. Okay, and that's 2 divided by 11. Okay. So these had, the difference from each mean was the same, but in chemistry, the standard deviation was a bigger number. Okay, so they were kind of spread out more. So actually, his z-score is a little bit smaller. So math is the one. Kind of makes sense that it's in the math. That's pretty good. Because okay, take a look at the next one. This is how, as I said, professors at university might be adjusting marks. So marks on a math exam at a university were found to have a mean of 52 with a standard deviation of 12. A professor who thought the exam was too difficult decided to adjust the original marks by raising the mean to 65. So that's all he did, was raise the mean to 65, then everyone would get adjusted the same. Okay? And that's kind of like what we do for mark adjustments in our math classes. But he also wanted to reduce the standard deviation to 10. So they spread out, say, this far right now. Now they're going to be closer together. Okay, so that's going to could move some of the higher a little bit lower, but certainly some of the lower a little bit higher, right? So the z-scores have to remain unchanged, but the other values do change. So what would the new mark be for a student who received an original of 34? So you want to think about for original of 34, z-score for 34. Okay, where does that person that earned a 34 stand in the class? So 34 is his or her mark, minus the mean, original mean on the test was 52, original standard deviation was 12. It's going to be a negative z-score because it's a mark below the average. Okay. So then you want to find the mean y. So think about it. I'm just going to copy out that formula again here. Sorry. Okay, so that's the formula that we've been using. We now know this. Okay, this is going to be mu. This is going to be mu, and we want to find what that is. So really, we're using the same formula, but rearranging it. So if I rearrange this, I would get Z sigma equals X minus mu, and then solving for X, that's what I would get. So my new value for 34, I'll take my new mean, and I add negative 1.5 times the new standard deviation. So I'll call this X mu is going to be the mean, which is 65 plus negative 1.5 times the new standard deviation, which is 12. And voila, the student passed. There would still be students failing though, right? Because if z-score would be 1.5 and negative, maybe 1.5, there's still more below, right? Because in a normal distribution, it goes at least to negative 3. Okay, so we still be failing the students, but that student now passes. Okay, last part. Again, properties of z-scores. So we talked about these, they're just summarized there. Z-score for a data value describes the number of standard deviations above or below the mean. So it could be negative, it means it's below the mean. Positive, it's above the mean. Z-score table, you don't have to worry about this. You worry about this for the z-score calculation, because before we allowed graphing calculators, we weren't allowed a graphing calculator that had a program in it, then we needed some way of calculating all of this, right? So they're tables of values that you could use to look up what the area is underneath. Now it's all stored in your calculator. Basically, like the ratios are all stored in there. All the normal distribution values are stored in there. Okay? It's possibly 4. So z-score processing your calculator gives the area under the curve to the left of the z-score, or the percentage, right? You can convert it to a percentage. Or the probability that a randomly chosen data value, okay, you can also consider it as probability. Remember that the mean, median, mode, z-score of 0. Okay, so now it says in these examples, we're not going to do all of them. It says use the z-score tables. We're not going to use the tables. We're going to go to using our calculator now. The steps for the calculator are on the back. You need to refer to them. Just follow what I'm doing, okay? So, if we're asked to calculate the area, A means area, that's for the z-score of -3. So it's often nice when you're doing work for these questions to do a little bell curve, right? With a vertical, horizontal axis and a vertical through the middle, okay? -3 then would be about there, right? And we want to find the area. So when it gives just one value, it's always meaning from the left. You might find different areas, but if it just gives you one z-score, it means from the left. Just like you read a book, left to right. Okay? So in your calculator, okay, so get out your calculator. If you don't have one, you can use to share it with someone so you can see how to do it. Bars is what we use to get y variables. On the actual calculator is distributions. So we call this a normal distribution. So you're going to go second P box. And you'll notice normal PDF, normal CDF. These ones are always PDF. Never use the CDF. Okay? So, enter on that. This is where it's different depending on what version of the calculator you have. Okay? Who has what I have? Lower, upper, middle, sigma, and up. Okay? Who has an actual normal distribution graph shown of the curve? Not a new one. Oh, that means CDX. Normal CDX. Normal CDX. Well, I'm the last one. You don't do the first one, you do the second one.
Okay, so CDF. No.
Never PDF. I'll show you what to do. Okay. Okay, so lower here, if you get these prompts, a couple of you don't have the prompts. Okay, what to fill in. So who does not have lower, upper? 1, 2, 3, 4, 5, 6, 7. Okay, so lower, what this means is where's the lowest x value in this graph? Well, remember we said this goes to negative infinity. There's no infinity symbol in your calculator. So we go negative 1. E means times 10 to the 99. That's 98 decimal with 98 zeros and sorry, that's negative 1 times 10 to the 99. So, what did I call that? Something really negative. Okay? If you don't have that, your bracket is open and you enter that. If you want to enter it as negative 1 times 10 to the 99, you can, or you use that E. Okay? In any case, everyone has to have that. Enter on that. Upper boundary. Now we're going to negative 3. Okay? That's the right list. So enter negative 3. For those that don't have this, you need a comma in between. So this, comma, this. So those 8 of you that had your hands up. Okay? Mu is 0 for z-scores. Sigma is 1. Those are the default settings. Okay? And then notice what happens here. If I go paste, that's what those of you that do not have the prompts should have entered into your calculator. Okay, so I'll come around for those of you that have different ones. And then you can just press enter on that if you want. Any of those prompts? Okay, so if I enter on this, that's what is labeled on that official normal distribution, right? The calculator's done it for you. That's why I said you don't have to memorize. Okay, if you look back on the previous page, for the area less than 3 deviations to the left, it's 0.0013 or 0.13%. So this is 0.0013. Okay, when it's rounded, or you can multiply to 100%. Okay, so this will be okay, and you can just label that area. So now do the same for the next one. It'll save most of it. So just change your upper boundary. Unless you have an older version of the calculator. Go like second and yes, some people can. Maybe second and third for everyone who will. You push her up. No, but no, second and third. Okay, yeah. So if you're doing a whole bunch of these, yeah, if you have an older calculator, do the second and enter, which is as opposed to second negative, which is the answer. Right. Yes. Okay, and remember, that's the sum. So in your chart, if you add 0.0013 and 0.0215, you get 0.0228, which is that. Right? So your calculator is doing it for you. Okay, so you can do the next one on your own. You can do example 6. I want to get to the ones that are areas in between here. So, so here, this one, 1.78. So again, that's the area to the left of 1.78. So like somewhere here. Same process. But let's take a look at this one. So Z greater than 2.61. So 2.61 is going to be about here. And we want the area greater than that. Okay? So on your calculator, it's you have to change your boundaries, right? So we go second distribution, normal CDF. Now our lower boundary is the Z-score, so 2.61, and our upper boundary is positive infinity, so 1 times 10 to the 99, Now, really, if you went 10 to the, I forget where it will cut off, it really depends on the decimal places. But 10 to the 99 is the biggest possible value your calculator can handle, so that's why we put it in. Okay, the closest to infinity that your calculator uses. In any case, this is your lower, and positive 1 is your higher. So those will lower to higher, and that will be 0.0045. Now, it says as a decimal and as a percent. So, multiply that by 100 in your calculator. 45.27, you can get a little bit more accurate. Two decimal places. Okay. Then these ones have, they're not going to infinity. Yep. Oh, what did I do? Yeah. Could be 0.45, yeah. I don't know, I don't find it that way. Yeah. Thank you. So next one, no infinity in these ones. Okay, so distribution, normal CDF, and now we're going from lower, negative 1.83, to higher, 2.65. So what's that? That's kind of like here to here. Okay, and then the last question is doing the opposite. Given now in the last question, the percentages are given to you, and you need to come up with a z-score. Okay? So, in the last ones, we were given the z-scores. Now we're doing the opposite, or the inverse. So get out your calculator, go to your distributions, and look underneath normal CDF. You see in norm. Let's say for inverse form. Okay, so it's doing the opposite. So on my calculator, it prompts me, and it asks me what the area is, and in there is 0 and 1. You can change that with actual data values. We do that totally. But it prompts me for the area. In older versions, that's what you're going to have to put in first. Okay? Now, the area that it's asking for assumes it's going from the left of the normal distribution. Although I think some newer calculators might say left tail or right tail. So who has some of those? Okay, so that's slightly different. Again, it's kind of like a left down and right down. So you might have to do a little bit less work. These ones are the same. So if the area is shaded from the left, everyone's is the same. Okay, the area is, in this case, you either include the percent symbol, which I wouldn't bother because it's hard to find in the graphing calculator. Just convert that to a decimal. Okay. If you notice how that's, if you have an older version, that's what you put in first. The area, comma 0, comma 1. So those of you that have the older version, area, comma 0, comma 1. Your z-score is negative Doesn't say what's around 2. We'll go to 2 decimal places. That's your z-score. You can get a positive z-score, then think about it. It'd be on the left, right? So you can move it up. Okay. Next one is on the right. Okay? So those of you that have the newer ones that have a tail on it, pause for a sec. You can probably figure it out. This one here, in our version of the calculator that I'm using, or the old version, the area that you put in is assuming it's from the left. Okay? So if I were to do that now, and put in 0.1492, it's going to give me a negative z-score. What do we know about this value here and this value? This is 14.92. What do we know about those two? Yep, opposite sides. Yep. So what the calculator gave me is this one. So I just have to change the sign. So this z-score that I'm looking for will be positive. Alright? So you can multiply this by negative 1. If you really need to do that in the calculator. Okay. Alternatively, you could say, okay, if this is 14.92, then this percent here is 85.08, and you could go distribution of that, because that is going from the left. Okay, so 0.8508. And it would be positive right away. This way is a little bit faster, right? You realize that. Symmetrical on both sides. Are you guys good with the tail? Those of you that have the newer one? Kind of pretty obvious, right? Yeah. Then, this one here, if I put in distribution, inverse norm of 0.2580, notice what it gives me. A negative. That doesn't make sense. Okay? Again, it's assuming that you're going from left, negative infinity, to the z-score. So that's not going to make sense. It's not going to make sense to just change the sign of it. So I would think about it. What's the percent here, the area underneath in that part? 50%, 0.5. So this total here will be 0.7580. 0.5 plus this. Just do that in the calculator. So here's 1, 0.7580. And it's 0.70. Positive, which makes sense. Okay, and then this one, same kind of deal. So, couple of ways. You have to find both z-scores here. All right, you know this area and this area. So, basically, you could say, you can go, okay, we get this one, add these together, and subtract from 0.5 to get this area, and then you could add on this to get this. So here, to get this area, this is going to be 0. Sorry, it's going to be 0.5 minus 0.1293 minus 0.2145. Okay, 0.5 minus, okay, I entered that correctly. So this part here is 0.1562. Okay. So, inverse norm. On a test, actually, you pick the written response. Just show me, you don't have to do it vertically, you can just do that graphic part of it. So, inverse norm there will be 0.1562. Negative 1.01. And then, this part